Today we're going to introduce a new topic, scalar fields. A scalar field is just a function that assigns every point in space a scalar value, that is, a number. As an example, you could imagine the temperature at every point in Australia. That's a scalar field because it assigns a number, the temperature, to every point in Australia. Another example might be the air pressure at every point in this room. Now, in engineering applications, we'd like to know certain things about scalar fields. For example, extreme values, maxima and minima. Where is the air pressure highest in the room? Where is the temperature maximum in Australia? The approach that we're going to take is quite similar to the approach we took for finding max and min for functions of one variable. Although, as you're going to see, there's going to be new situations that arise because we're dealing with functions of more than one variable. So we're going to start by looking at the method used for calculating max and min for functions of one variable, and then see how that has to change when we deal with functions of more than one variable. So I've drawn here a function of one variable, f of x. And you can see that it has a fairly clearly defined maximum and minimum value. We know there's a max and min there because that's where the function levels out. If you like, that's where the function has a derivative equal to 0. So this point here, the function is neither increasing or decreasing. We know that this is going to be a stationary point or a critical point. And likewise, we know that this point here is also going to be a stationary point or a critical point because the derivative of this function at that point is equal to 0. So that's the first step in identifying max and min. We need to find the critical points or the stationary points. But of course, that's not enough because just knowing where the critical points are doesn't tell us if those are max, min, or something completely different. To do that, we need to look at the second derivative. So we can identify whether the function is a maximum or a minimum by looking at its curvature, that is, its second derivative. So for example, looking at my minimum over here, you can see that locally it looks like a valley. I could draw a little curved line there indicating that this is a valley. I'm going from a downward slope to no slope to an upward slope. So the second derivative of the function at that point is positive, and that implies that it's a minimum value. It's a valley. Likewise, in this case here, you can see that locally it looks like a hill. Its second derivative will be negative, indicating that I'm going from a function that's sloping upwards to sloping to no slope to sloping downwards. This is a maximum. Of course, there was another possibility when my function has a second derivative equals to 0. We call that a stationary point of inflection. As we're going to see, there's an analogy here for functions of more than one variable to points of inflection. Okay, so the approach in 2 dimensions is quite similar. It's a 2-step process. The first thing we do is we look for the critical points by setting the first derivative equals to 0. Now, of course, I have a function of more than one variable, so I'm going to have to set every first derivative equals to 0. So our first step in the process is to look for the critical points. And again, those are points where the first derivative with respect to x is equal to 0, and the first derivative with respect to y is equal to 0. So you see that that's already given us something new, because that condition there, that the first derivatives are equals to 0, is going to give me two equations for my unknown variables, x and y. Now the solutions to those equations will give me all of my critical points. The next step then is to use the second derivative test to classify my critical points. So those can be local maximum, minimum, or the new possibility, or a saddle point. So let's see what those look like and how we can identify them using the second derivative test. So let's start off with the local maximum and minimum. I want you to think here about looking at a topographic map, that is a map of heights of a geographical area. Now we know that the heights are all indicated by a line, so that contour indicates points on the map that are at the same height. If I was looking at a mountain, what would that look like? Well, it would look like nested contours. You can see that the highest point on my mountain will be at the center here. And then as I move away from the center, I'm going downhill and I'm crossing contours, lines of equal height. Likewise, if I was looking at some hole in the ground, a valley of some kind, then the lowest point again would be the point in the middle, and it would be surrounded by contours of equal height getting higher and higher. So if I start at the middle and I walk in any direction outwards, I'll cross contours, I'll be going uphill. So you see that for local maxima or minima in 2 dimensions, you always have closed contours around the maximum or minimum value. You always have closed contours around your critical point. So that's an identifying feature for local max and min. Now, how do we identify closed contours? Well, I'll show you the test for that in just a moment. But let's say we now know that there's closed contours. How do we know whether we're looking at a maximum or a minimum? If I was just looking at a map like this, then I wouldn't be able to tell whether I'm looking at a maximum or a minimum. Well, what we can do is we can look at, is the second derivative positive or negative, just like we had for functions of one variable. If the second derivative is negative, then we know we're looking at a maximum. We're increasing and then decreasing. If the second derivative is positive, we know we're looking at a minimum. Then we're decreasing and then increasing. The problem, of course, is that we have 2 directions to go in. I could go in the x direction and look at the second derivative there, or I could look in the y direction and look at the second derivative there. Is that positive or negative? In fact, it doesn't matter because I've got closed contours. So if the second derivative is negative in the y direction, then the second derivative will be negative in the x direction as well. So we have a case where it doesn't actually matter whether you look in the x or the y direction, so let's just pick the x direction. So just as in the case for functions of a single variable, if the second derivative, this time the partial derivative, is negative, it means that I have a maximum. And if the second derivative is positive, it means I have a local minimum. And of course, I could equally well look at could also use the second derivative with respect to y, if I wanted to. It's not going to make a difference because, again, it doesn't matter which direction you're going in, x or y. Because you've got closed contours, the second derivatives will both be the same in each direction, the same sign. Okay, so I said that local maxima and minima always have closed contours. And if I know they've got closed contours, my function has closed contours around the critical point, then I can use the second derivative test to figure out whether I'm looking at a maximum or a minimum. But what happens if I don't have closed contours? What would that look like? Well, that's called a saddle point, and it looks like this. It's the case when we don't have closed contours. And instead, I've got in one direction a maximum, and in the other direction a minimum. So what would that look like if I was looking at a topographic map, a geographical map showing lines of constant height? Well, it would show that I have open contours. Like that. So you could imagine that this point here is high up. This point here is high up. But in between, I've got a low point. So if I look in this direction here, we're talking about a minimum, a local minimum. It's a low point between two high points. But if I'm looking in the opposite direction, let's say that this point here is low, and this point here is low. Then if I'm walking in this direction, I start off low, I go uphill to reach this point, and then I go downhill again. So in this direction, I'm actually looking at a maximum. So it's a maximum in this direction, and it's a minimum in this direction. So maximum walking in that direction, or a minimum walking in that direction. So you might like to think about this as almost like you're walking along a ridge between two mountains. So I'm starting at the bottom of the ridge, or the bottom of the pass. I'm climbing up towards this low point between two high mountains, and then I'm crossing over and going downhill again. It's a pass between two mountains, or a ridge between two mountains. Okay, so how do we identify that what we're actually looking at is something that has open contours like this, is a saddle point? Well, what we're going to do is use a new test. It's called the second derivative test for functions of two variables. And it involves the following function. D is equal to the second derivative of f with respect to x, second derivative of f with respect to y, minus the mixed derivative. So I've got d is equal to fxx times fyy minus fxy squared. So again, because I've got a function of two variables, I can have this mixed derivative with respect to x first, followed by the derivative with respect to y. For most functions that are pretty well behaved, it doesn't matter what order you take these in. Okay. So how can we understand where this formula comes from? Well, one way to think about it is that imagine that I have no mixed derivative. Imagine that my function is perfectly aligned along the x direction and the y direction. That is to say, if I'm walking in the y direction, So rotate this whole picture here so that walking along the y direction gives me this low to high to low, and walking in the x direction gives me this high to low to high, right? So in the y direction, I'm actually looking at a maximum, and in the x direction, I'm looking at a minimum, right? That defines a saddle point, where I can walk in one direction to get a maximum and walk in the other direction to get a minimum. So what that means is that because I've got a minimum for in the x direction, fxx is actually positive, right? Minimum, I have the second derivative is positive. Whereas for fyy, when I'm walking in the y direction, I'm actually looking at a maximum. So fyy would be negative. So I have a positive number times a negative number. And I said, ignore the mixed derivative term here. And the reason I can is because I've rotated everything so that it aligns with the x and y coordinates. So I've got a positive number times a negative number that gives me a negative number. And that's going to actually be what defines a saddle point. If I have that my function d is less than 0 at the critical point, it means I have a saddle point. It means I have open contours. On the other hand, if I have d is a positive number, it means that I have closed contours, which implies that there is a local maximum or minimum. Now, I still don't know whether I'm looking at a maximum or a minimum yet, because I need to look at the individual sign of fxx or of fyy to be able to figure out whether I'm looking at a maximum or a minimum. But because d is positive in this case, I know that I'm looking at the closed contour case. Or if d is negative, I'm looking at the open contour case. So that's actually going to be the first thing that we do when we're trying to categorize our critical points. We're going to look at whether the contours are open or closed by looking at this function d evaluated at the critical point. If it's negative, I know I'm looking at a saddle point, and I don't need to do any more. If it's positive, then I know I'm looking at a maximum or a minimum, and then I have to look at the derivative with respect, the second derivative with respect to x or the second derivative with respect to y to figure out whether it's a maximum or a minimum. Now, so far, I ignored that mixed derivative term here. And again, I pointed out that the reason I can do that here is because in my little thought experiment, I rotated the coordinate system so that the ridge line here aligned with the y direction and the ridge line here aligned with the x direction. And because, of course, there's no guarantee that those ridge lines will actually align with the x and y directions, then I do have to include this term here. So that's what's being included there to account for the fact that these points might be aligned in different directions. One last thing to point out here is that if I have, again, let's imagine I'm looking at a local maximum or minimum, notice that I can get the derivative with respect to xx is a positive number or a negative number, and the derivative with respect to yy is a positive number or a negative number, right? So if this is a local maximum, then both of these will be positive. If this is a local minimum, then both of these will be positive, right? So the point is that this will only ever be positive if we're looking at a local maximum or a minimum. Positive times positive is positive, negative times negative is positive. So we don't have to worry about whether or not we're looking at a local maximum or minimum. This formula will take care of that for us. Okay, so in the process of looking for these critical points and then categorizing them, what we're going to see is that it involves solving a number of equations simultaneously. And we have to be very careful that as we solve these equations, we don't accidentally throw away legitimate solutions, correct solutions, by dividing both sides of an equation by something that could be equals to 0. So we'll see examples of that in the next couple of examples. Let's start by looking at example 1. In this case, we've got a function f of x y equals to minus x squared minus y squared minus 6x plus 4y plus 5, a function of two variables. I'd like to be able to find and categorize the critical points. So the first step I'm going to take is to identify the critical points, or solve for the critical points, by taking the first derivatives with respect to x and y of that function. So I've got that the partial derivative with respect to x is equal to minus 2x minus 6, and I'm setting that equals to 0. I'm looking for where the function is neither increasing or decreasing. It's stationary in the x direction. Now notice that that gives me an equation for x, that I can solve that immediately. So I get x is equal to minus 3. So that gives me one of my coordinates, one of my variables. I also need to find the first derivative in the y direction, and also set that equals to 0. Look for where the slope in the y direction is neither increasing or decreasing. Again, I get an equation for y, which I can solve to get y is equal to 2. So you see, I get x is equal to minus 3, y is equal to 2, and so I get the point minus 3, 2. Now, in these kinds of problems, we still need to identify what the maximum value is, or the minimum value is. So I need to find out what f is at minus 3, 2. So let's do that right away. Sticking in x is equal to minus 3, y is equal to 2. I get minus times minus 3 squared, minus 2 squared, minus 6 times minus 3, plus 4 times 2, plus 5. And that's going to give me 18. So my critical point is at x is equal to minus 3, y is equal to 2, and f is equal to 18. Now, of course, that's not enough. I still need to be able to categorize what that critical point is. Is it a local maximum, a local minimum, or a saddle point? So to do that, I'm going to look at the second derivative test. And first things first, let's calculate what d is. So remember that d was given by the second derivative with respect to x, second derivative with respect to y, and I'm going to need the mixed derivative as well. So let's calculate all of those at my critical point. So the second derivative with respect to x is going to be given by minus 2. The second derivative with respect to y is going to be given by minus 2. And the second derivative, the mixed derivative with respect to x and y, is equal to 0. So those are what the values of the second derivatives are at my point minus 3, 2. So let's use those now to form d. So d is equal to fxx fyy minus fxy squared, which is equal to minus 2 times minus 2 minus 0 squared, which is equal to 4. That's a positive number, which means that I'm looking at a local maximum or minimum here. I've got closed contours. D is a positive number, which tells me it's a local maximum or minimum. Now, which one is it? Is it a local maximum or minimum? To answer that question, I need to go back and look at those second derivatives. So I've got the second derivative with respect to x is equal to minus 2, and the second derivative with respect to y is equal to minus 2. So the second derivative is negative, which implies that this is going to be a local maximum. So you saw the steps in that process there. First of all, I needed to find the critical points by setting the first derivatives equal to 0 and solving the resulting simultaneous equations. Next, I needed to figure out whether I was looking at open or closed contours, if I was looking at a saddle point or a local max-min. To do that, I calculated the second derivatives and formed the function d. I found in this case that the function d was positive, which tells me I've got closed contours and it's a local maximum or minimum. And the final step was to go back and look at those second derivatives to tell whether it's a maximum or a minimum. So let's take a look at what that function actually looks like. So it's shown here. There is a maximum point at -3, 2 with a value of f is equal to 18. So this is shown in 3D, and this is again showing like it's a topographic map. So these lines here are contours of equal height. Let's look at a more complicated example. The problem is the same: find and classify the critical points of this function. So let's start by calculating the first derivatives. So I've got the derivative with respect to x is equal to 4 times y minus 2xy minus y squared. We're going to set that equals to 0 to get one equation for x and y. The derivative with respect to y is equal to 4x minus x squared minus 2xy equals to 0. So now I have two equations for two unknowns. Let's simplify these a little bit to make life a bit easier. Let's take out a common factor of y in the first case. That leaves me with 4 minus 2x minus y equals to 0. And likewise, the derivative with respect to y, taking out a common factor of x. The other factor is 4 minus x minus 2y, and that's all equals to 0. So you see now I've got these two equations to solve, and I'm solving them simultaneously. Right? So I want to find solutions that satisfy both of those equations. Let's take a look at the first equation. You see that I've got something times something equals to 0. Y times 4 minus 2x minus y equals to 0. Now, whenever I have a situation where I have something times something equals to 0, then I know that at least one of those things must be equals to 0. So if I have something times something equals to 0, at least one of those things must be 0. So I have that either y is equal to 0 or 4 minus 2x minus y is equal to 0. Likewise, with my second equation here, I have again something times something equals to 0. So one of those things must be equals to 0, which gives me two possibilities. Either x is equal to 0 or 4 minus x minus 2y is equal to 0. So you see that I've got a couple of different possibilities. Now I have to have both of these equations satisfied. This is a simultaneous set of equations, so both of them have to be satisfied for the particular values of x and y that we find. So that means that either y has to be equals to 0, or 4 minus 2x minus y has to be equals to 0, and one of these things has to be satisfied. X is equal to 0, or 4 minus x minus 2y is equal to 0. So you can see that I can actually write out all the possibilities. Y is equal to 0 and x is equal to 0. Y is equal to 0 and 4 minus x minus 2y is equal to 0, and so on. Let's write those out. The first possibility is y equals to 0 and x is equal to 0. So again, I'm using one condition from this line and one condition from this line. So that implies that my critical point will be at x is equal to 0, y is equal to 0, and we also need to know what the value of f is, and if I substitute that in, we get f is equal to 0 at that point. The next possibility was y is equal to 0 and 4 minus 2x minus y is equal to 0. This is going to imply that if I substitute y is equal to 0 in there, you can see that I get 4 minus 2x is equal to 0, which gives me x is equal, I made a mistake, sorry, I took the wrong equation. 4 minus x minus 2y, there we go, is equal to 0. So that implies when y is equal to 0, that implies x is equal to 4. We had y is equal to 0. And if I substitute x and y equals to those values into f, I find that I get 0 again. Let me just point out where I made my little mistake there. Remember that I always want to have one condition from the red equation, which gave us those two red conditions, and one condition from the blue equation. Okay? So the blue equation told us that either x was equal to 0 or 4 minus x minus 2y was equal to 0. So when I'm looking at y is equal to 0, I can even underline these guys to show I'm selecting one from here and one from here. You see that I need to pick either this condition or this condition. So y is equal to 0 and x is equal to 0, or y is equal to 0 and 4 minus x minus 2y was equal to 0. So let's continue to underline in different colors like that, just so we don't make any more mistakes. The third possibility is the red condition, 4 minus 2x minus y is equal to 0. Underlining in red just so we don't get confused. And one of the blue conditions. So let's pick the first one, x is equal to 0. Let's underline it to show that that's satisfying the blue equation. And I'm solving those two simultaneously, so substituting x is equal to 0 into here gives me 4 minus y is equal to 0, which gives me y is equal to 4. So x equals to 0, y is equal to 4, and if I substitute x and y equals to those values into fxy, I get 0. And then I've got my last possibility, which is 4 minus 2x minus y equals to 0. And 4 minus x minus 2y equals to 0. So one solution to the red equation and one solution to the blue equation. So we're going to solve those two simultaneously. Probably the easiest way to do that would be to multiply the second condition by minus 2. So what I did there was I took my blue condition by minus 2. And I'm going to add together those two equations. You see that the two x's cancel. 4 minus 8 is minus 4. Minus y plus 4y is plus 3y, which I can solve to give y is equal to 4/3. And let's go back and solve for x. X, using the blue condition up here, x will be equal to 4 minus 2 times y. which is 4 minus 8 over 3, which is 12 minus 8 over 3, which is 4 over 3. So I get a critical point at x is equal to 4/3, y is equal to 4/3, and I need to calculate what the value of f is at that critical point, and that's going to be given by 64 over 27. I'll let you show that yourselves. Okay, so we have all of our critical points now. Notice that I ended up with 4 different critical points. 1, 2, 3, 4. So I was solving 2 sets of equations and ended up with 4 different points. And you notice that I was very careful to deal with all of the different possibilities. I didn't divide out y at this point, or I didn't divide x out at this point, because those can be equal to 0, and those are indeed possible solutions here. So now I have my 4 points. I have to check what those are. Are they max, min, or saddle points? So let's calculate my second derivatives to do that. The second derivative is going to be equals to going back and looking at where I calculated my first derivatives up above. So my first derivatives are given here, so I can calculate my second derivative straightforwardly from that. Second derivative is going to be given by minus 2y. That's the second derivative with respect to x. The second derivative with respect to y will be given by minus 2x. And then I've got the mixed derivative with respect to x and y. So I can either pick the first derivative and take its first derivative with respect to x and take its derivative with respect to y, or the other way around. So first derivative with respect to y, take it. First derivative with respect to x, take its derivative with respect to y. Get 4 minus 2x minus 2y. So those are my second derivatives. Now I need to actually go and put in what each point is. So the first point was x is equal to 0, y is equal to 0, f is equal to 0. So let's substitute those in and calculate what my second derivatives are, and then what the function d is. So fxx in this case will be equals to 0, fyy in this case will be equals to 0, and fxy will be equals to 4. So that means that d will be equals to fxx times fyy minus fxy squared, which is 0 times 0 minus 4 squared, which will be minus 16. So that's a negative number, which implies that this is a saddle point. Now with saddle points, I don't need to do anything else. I don't need to identify whether it's a max or a min. I know it's a saddle point. Next case. This is the case when x is equal to 4, y is equal to 0, and f is equal to 0. So the second derivatives, fxx is equal to minus 2 times 4. fyy is equal to minus 2 times, I got those backwards. fxx is 0, fyy is minus 2 times 4 is minus 8. And fxy, again, is going to be equals to 4 minus 2 times 4, which will be minus 4. Okay. So what's d? D is equal to fxx times fyy minus fxy squared, which will be minus 16. Again, that's negative. So again, this is a saddle point. Third possibility. 0, 4, 0. Calculating second derivative with respect to x is going to be equals to minus 2 times 4, which is minus 8. Second derivative with respect to y is equal to 0, and the mixed derivative fxy is equal to 4 minus 2 times 4, which is minus 4. So d is equal to minus 8 times 0 minus minus 4 squared, which is equal to minus 16. Again, that's negative. So again, I get saddle point. So far, everything has been a saddle point. I haven't had any cases where there's been closed contours. Let's look at the last case. This is the case when x was equal to 4/3, y was equal to 4/3, and f of xy was equal to 64 over 27. So fxx is equal to minus 2 times y, so that's going to be minus 8/3. fyy is equal to minus 2 times x, which is minus 8/3. And fxy is equal to 4 minus 2 times x minus 2 times y, which is going to be given by, let's see, 4 minus 8/3 minus 8/3, which is equal to 12 minus 8 over 3, so that's going to be minus 4/3. So what is d in this case? D is equal to fxx times fyy times minus fxy all squared. So we end up with minus 8 times minus 8 is equal to 64. Over 3 times 3 is 9. Minus 4 squared over 9. And that's going to be equals to 64 minus 16 is 48, which is a positive number. So I have that d is a positive number. That means that I've got closed contours here, dealing with a local maximum or minimum. Now let's remind ourselves how to figure out whether it's a maximum or a minimum. We look at the second derivative. We can pick either the second derivative with respect to x or the second derivative with respect to y. They'll always be the same sign whenever you have closed contours like this. So let's look at the second derivative with respect to x. You notice that it's a negative number. So because f of x is negative, and I've got d is positive, I've got closed contours, this implies that I have a local maximum at 4/3, and the value of f at that point is 64 over 27. So in this problem, we saw that we ended up with 3 saddle points at 0, 0, 4, 0, 0, 4, and 1 local maximum. So let's take a look at what that looks like. In this particular function, there's a maximum at this point here, and at all these other points you get these saddle points. So you can see that a little bit easier when you look at the contours. You can see that at this point here, if I move in this direction, I'm actually moving downhill in either direction, but if I move in this direction, I'm actually moving uphill. Likewise here, if I move in this direction, I'm moving downhill in either direction, but if I move in this direction, I'm moving uphill. So these are all saddle points, whereas this point here, no matter what direction I go in, I'm always going downhill. That's a local maximum. Last example, example 3. We're looking at the time, flight time from Sydney to Los Angeles. If you're burning fuel containing A milligrams of antifreeze and N milligrams of naphtha. So aviation fuel contains both antifreeze and naphtha, and the different combinations that you make give you different thrusts and therefore different amount of time taken to fly from Sydney to Los Angeles. So the first thing we're asked to do is to find out what the flight time is if there's no antifreeze or naphtha. That is, there's no additives at all. What do we get? So we're just going to, in that case, set in A is equal to 0 and N is equal to 0. So T at A equals to 0, N is equal to 0 will be given by 0.005 times naught squared plus 0.005 at naught squared minus 0.03 times 0 minus 0.05 times 0 plus 14. So the only thing there that hasn't got a 0 multiplying it is the 14. So the flight time from Sydney to Los Angeles, burning a fuel of pure kerosene, is 14 hours. So that's no additives at all. That's the first part of the question. Second part is, what is the flight time when I'm burning fuel containing 2 milligrams of antifreeze and 4 milligrams per liter of naphtha? So substituting in A is equal to 2. And N is equal to 4. Sticking all that into your calculator, you end up with 13.84 hours. Or roughly 13 hours and 50 minutes. And 24 seconds. So how close is that to the ideal mix of antifreeze and naphtha? Well, to do that, we need to find the minimum value of T. So let's figure out what that is. So T, take its first derivative with respect to A. T sub A is going to give me, let's see, 0.05 times 2A, which is 0.01 times A, plus 0.005 times 2N, which is 0.01 N. Oh, sorry. Ahead of myself. 0.01a minus 0.03. Set that equals to 0. I can solve that immediately to get a is equal to 3. First derivative of t with respect to n is 0.01 n minus 0.05. Set that equals to 0 and solve to get n is equal to 5. So what this is telling me is that there's a critical point at a is equal to 3, n is equal to 5. I'll let you check yourself that this is a minimum value. Again, you're going to use the second derivative test to do that. I'm just going to assume that this is a minimum. So what is the time taken at a is equal to 3 and n is equal to 5? Well, if you substitute that in, you'll get 13.83 hours, which is about 13 hours 49 minutes and 48 seconds. So you can see that I've gotten quite close to the ideal time. So either I've gone 13 hours 49 minutes 48 seconds compared to 13 hours 50 minutes 24 seconds. So let's take a look at what this function looks like. So here again you've got the function in 3 dimensions. The minimum point is shown here, or shown in as a contour plot. You can see that I've got the minimum surrounded by closed contours.